Part 2, this is for questions 11 to 20. Question 11, boron trifluoride reacts with ammonia to form a single compound with a simple molecular structure. So this is the reaction here. And they are saying which row describes how bond angles change during the reaction. Now, boron trifluoride, we are having boron here, then fluorine, and then there is fluorine here, and then another one here. This one is actually electron deficient. Okay, boron is in position 3, so 2 to 1. This one would have been an ionic structure, but it attains a covalent character. Okay, and you find that because of the stronger attraction between these two ions, okay, in here there is going to be overlap of orbitals. I'm not going to go deeper into the chemistry, but it is going to be bit covalent, so it is going to be electron deficient. That means this is 2, 2, and 2. Those will be 6, right? Now, if those are 6, then we are going to have 2 more. It can attain 2 more electrons to have a full octet. You see that? Now, what is going to happen is that ammonia, by the way, this angle here is 120 degrees, even here, 120 and 120. This is trigonal planar, okay? Trigonal planar structure. Then when we come to ammonia, using valence shell electron pair repulsion theory, so if there is a lone pair here, the repulsion between the lone pair bond pair is bigger than the repulsion between bond pair. Why do we say bond pair? So there is an electron and an electron, so that is a bond. You see that? Now, even here there is a bond, so it's a bond pair. You see that? Okay, bond pair. This is a pair, and then this is a pair. So the repulsion in there is smaller than the repulsion between a lone pair and a bond pair. So in such a case, we are going to see that, first of all, if I take off these and I put, let's say, 1 here. So if it is tetrahedral, we know that the angle is 109.5. But now when you replace all of these ones, the angle is going to be the same, okay? But now, when we take away that bond pair and then we replace it with a lone pair, this lone pair here, the repulsion is going to be bigger than this one and this. So that means the angle here, which would have been 109.5, is going to reduce, and you find that the angle is going to be below 109. We can put 107, maybe 107 degrees. This is trigonal pyramid, not so? This is a pyramidal shape, so trigonal pyramidal shape. You see? Now, when these two react, what is going to happen? You are going to have this one will donate its lone pair of electrons to that. Are we there? When it donates, then now these ones, there is going to be a bond formed, and now they become 4. So there will be 4 for ammonia. There will be 4 for this one, boron trifluoride. Okay, for boron there. So that means I can have now something like this, then this, that, then again this, that. So you're going to have fluorine, then hydrogen. You see that? Now, when you look at the structure of this one, it is now tetrahedral. You see? So the angle is now going to be 109.5. It's the same here, the same here. Then it is the same thing. We are going to also have this way 109.5. The same here. Okay, it's the same here, the same here, the same there. So all of them now attain a what? a tetrahedral structure. You see that? That means from 107, the bond angle increases to 109.5. You see? So hydrogen, nitrogen, hydrogen bond. Okay, what are they saying? Hydrogen, nitrogen, hydrogen. This bond here has increased, not so. So if it has increased, then we have here and then here. And then fluorine, boron, fluorine, fluorine, boron, fluorine. It has moved from 120 to 109.5. So it has decreased. You see that? So we are going to look for decreasing. And it has to be here and here. So where do we see the two ticks? Here. That means our answer has to be a B. Question 12. The equation for the reaction of nitrogen with hydrogen is this one here. It is production of ammonia. It is an exothermic reaction. That is the Haber process. Which statement is correct? DHR is measured at 298 degrees C. No. It is at room temperature. So that is 298 kelvins. Okay. When you get to the 25, then plus the 273. You see that? 25 degrees C, then plus the 273. That is when you get the 298. But kelvins, not what? Degrees C. Okay. Then DHR is measured at 10 kPa. Yeah, pressure is 1 times 10 to the power of 5. This one can actually be 1. The real value of pressure, when you go to your calculator and then you go to where there is constant, okay? Constant, that is on button 7. So you press shift, then constant 7. So they're asking for the number. When you look at the back, there are those constants there. So you will find ATM, that is atmospheric pressure, the value there. So you press 40, it is on number 40. So when I press 40, then ATM comes, and then I press equals, it will bring that value. That is the one for atmospheric pressure, 101325 that I'm talking about here. But in standard form, it can be written as 1 times 10 to the power of 5. It can be given as 101. Then these ones, if you round off to 3 significant figures, then it will be that 000. Or you take this away and then you put K, kilopascals. That is the one here. So that has to be our answer here. Okay, at room temperature and pressure. That is the one there. Then DHR represents the standard enthalpy change for the formation of ammonium gas. No, here we are looking at 1 mole of a compound that is formed from its elements in their standard states. Yes, this one is in standard state, even this one is in the standard state, but here you are forming 2 moles, not 1 mole. So for standard enthalpy of formation, we are looking at 1 mole, right? So this is just the enthalpy of the reaction, not for formation. Okay, then here this one represents the enthalpy change when 1 mole of nitrogen reacts with 1 mole of hydrogen. These are even 3. That is very wrong. Question 13. Hydrogen peroxide decomposes into water and oxygen when a suitable catalyst is added. Let's write that equation. Hydrogen peroxide decomposes into water and oxygen. So I can put a 2 here to make oxygens 2, then plus the 2, there will be 4. So I'll put a 2 here. Oxygen becomes 4, even hydrogen is 4, as it is here. Then they are saying 20 cubic centimeters of aqueous hydrogen peroxide produces 600 cubic centimeters of, at room conditions. Now, here we're having 600 cubic centimeters. Okay, now we need to get the moles of oxygen. So since this one is done at room condition, okay, room conditions, we know that 1 mole of a gas at room temperature and pressure occupies 24 liters or 24,000 cubic centimeters. So that means if we know that 24,000 cubic centimeters, okay, of volume is occupied by 1 mole of gas. That means the 600 cubic centimeters of volume would be occupied by 600 times 1, then divide by this one here. So usually we just get the volume there, then you divide by this one, the molar gas volume. You see that? And if I take this one, and that, 6 goes into here 4 times, so this will be 40. 1 over 40 will be 0.025. 0.025 moles. Now they are saying what is the concentration of aqueous hydrogen peroxide. Now we need to find the moles of this peroxide. Now look at the mole ratio. It is 2 to 1. That means if you're having 1 here, to get this 2, you multiply it by 2, not so? Okay, so we shall get 2, then times what we have gotten here, the 0.025, which is 0.05, not so? Moles. Now, after getting that, these moles here are contained in 20 cubic centimeters. So how about in a liter? So I'll say 20 cubic centimeters of this one contain 0.05 moles. Then how about 1,000 cubic centimeters will contain, we shall have 0.05, then times 1,000, then we shall divide by the 20. You see that? Let me try to shift this one a little bit there, such that it is seen clearly. So what do we get here? We have 0.05 times 1,000, then we divide by 20. Then this one gives us 2.5 moles per liter. So which is B here. Then question 14, when 0.15 grams of an organic compound is vaporized, it occupies a volume of 65 cubic centimeters at 405 kelvins and 1 times 10 to the power of 5 pascals. Then using the expression PV is equal to nRT, that is for an ideal gas, okay? Which expression should be used to calculate the relative molecular mass of the compound. Now, first of all, pressure here has to be in pascals, okay? In pascals. Well, that is the same as Newton per meter squared, because pressure is equal to force over area. So force is in newtons, then area is in meters squared, the SI units. That's why it is Newton per meters squared. And then we are taking the pascals. It's okay, because pressure can also be in terms of millimeters of mercury. It can also be in atmospheres, you see. So that is that. What else do we have? Volume has to be in meters cubed. Now this volume here is in centimeters cubed. Now you know that 1 centimeter, we have to convert to meters cubed. 1 meter, or maybe let me begin with what I have here. 100 centimeters, it is equivalent to 1 meter, not so? Now when we cube, we shall get this 100 cubed, then centimeter cubed will be equal to 1 cubed, and then meter cubed is that, which is the same as 1 times 10 to the power of 6, not so? Like that, which is equal to 1 meter cubed. So that means 1 centimeter cubed will be equivalent to 1 over 10 power 6 meters cubed, which is the same as 10 to the power of negative 6 meters cubed. You see that? So that means what I'm having here, if it is 65 cubic centimeters, then I'll get 65 and I multiply by 10 to the power of negative 6 to change it to meters cubed. And then temperature has to be in kelvins. Now PV is equal to nRT. What is N? N is mass, number of moles. So mass out of the MR, then RT. Now to make MR is subject to the formula. We shall cross multiply here, and then our MR is going to be M, then RT. Of course, after multiplying with this, then we shall divide through by PV. So divide by PV. Now, what is the mass? The mass is 0.15. Then times R is 8.31. That is the molar gas constant. Then times the temperature. Temperature is given as 405 kelvins. So if it is given in degrees C, remember to add the 273 to convert it to kelvins, right? So this is 405. And then we shall divide by the pressure, which is 1 times 10 to the power of 5. Okay. Then times the volume, which is 65, but it is in cubic centimeters. We have to multiply it by 10 to the power of negative 6, such that it is in meters what? Cubed. And when you look at this one here, you will find it here. 0.15 times 8.31 times 405, then this one here and that. So that means our answer is supposed to be D here. A washing powder contains sodium hydrogen carbonate as one of the ingredients. In a titration, a solution containing 1 gram of this washing powder requires 7.15 cubic centimeters of 0.1 molar sulfuric acid for complete reaction. So sulfuric acid here happens to be the standard solution. It has the known concentration here, okay? And also this volume here. The sodium hydrogen carbonate is the only ingredient that reacts with the acid. And then they want us to calculate the percentage by mass of sodium hydrogen carbonate in the washing powder. Okay, now let us write the equation of reaction. You have sodium hydrogen carbonate, just like sodium carbonate. It will react with sulfuric acid to produce a salt, which will be sodium sulfate, okay, then plus carbon dioxide and water. Now to balance this one, since we are seeing a 2 here, I'll put a 2 on this one here. Then the 2 multiplies the moles of carbon here, so it will be 2. Even here I'll put 2. But for sodium carbonate, of course, the number of moles of carbon dioxide is going to differ, okay? But they give the same products, okay? Then how about water? So here we are seeing for hydrogen, we are seeing 2 hydrogens plus 2 hydrogens, that is 4. And here we are having only 2, so that means I'm going to put a 2 here. How about oxygen? This is 2, then plus the 4, that will be 6, then plus 6 plus 4, that will be 10. This one is 6, then plus the 4, 10. Sulfur is 1, so balanced. Now, moles of sulfuric acid. This one is going to be, get this one here, 7.15 divided by 1000, then times the moles we are having here, 0.1. But this one, how you get it actually, it is this, just this statement here. It means that in 1000 cubic centimeters of solution, okay, this one here contains 0.1 moles. You see that? Of sulfuric acid. Or sulfuric what? Acid. Then how about the 7.15? So how about the 7.15? So this one here will contain, you have the 7.15, then times the 0.1 out of 1000. You see that? So you just need to get this volume, you divide it by 1000. Okay, so it has to be in a liter, such that you also multiply with the moles here that are in a liter. You see that? What will this one actually be? 7.15 times 0.1, then we are dividing by 1000. This one will give us 7.15, then times 10 to the power of negative 4, okay, moles. Okay, then from here, after getting the moles of sulfuric acid, which happens to be the standard solution, now we use the stoichiometric equation to get the moles of this other reactant that reacted. So from the mole ratio here, you can see it is 2 to 1 here. So since this one is a 1, how do we get a 2? We multiply by 2. So from the mole ratio, that means moles of sodium bicarbonate that reacted, this one is going to be equal to 2, then times this 7.15 times 10 to power negative what? 4. What do we get? The answer we have here, we multiply it by 2. Then we get 1.43 times 10 to power negative what? 3 moles. You see that? They want the percentage by mass of sodium bicarbonate. Now we need to get the MR of sodium bicarbonate. Sodium is 23, hydrogen is 1, carbon is 12, oxygen is 16, but there are 3 of them. This will be 48 plus 12, that will be 60. Then plus 24, isn't that 84? This one will give us 84. Now, you know that moles, number of moles, equal to mass over the MR. What do we need? Mass. So you cross multiply, get the moles here, then times the MR. Okay? So mass of sodium hydrogen carbonate would be equal to the 1.43 times 10 to power negative 3, then times the 84. This one here, we shall multiply by 84. You get 0.12012. 0.12012 grams. You see? But from here, they are saying 1 gram of this washing powder requires this. So, but this is the one that we are seeing that has reacted. That means this washing powder has gotten impurities. The only bicarbonate which reacted is this, and the whole of it reacted. So that means the percentage of sodium bicarbonate in that washing powder is going to be that 0.12012. Then we divide by 1 gram, then times 100. You see? Of course, this one will just shift here and we get 12.012, which is going to be 12%. So that is C. 16. The flowchart shows some reaction of nitrogen compounds. Gas 1, then plus the acid, you get salt 1, then you put the alkali, you get salt 2, and other products. And on the look of things, here they are saying which row identifies gas 1 and salt 2. We are seeing ammonia and then nitrogen dioxide. Now, ammonia is a basic gas. Are we there? Then nitrogen dioxide is an acidic gas. Okay? Because when you dissolve this one in water, you are going to get nitrous acid. I mean, it's not nitrous acid, it's nitric acid. Then this one, you are getting a basic what? A solution, weak base solution. That is, we call it ammonium hydroxide. Now, when you look at this one here, this is an acid, cannot react with an acid. This is an acidic gas, cannot react with an acid. That means the gas has to be ammonia. You see that? So I'll put off this one here. Now, ammonia plus an acid. Now, here we are seeing a nitrate. A nitrate comes from nitric acid. You see that? So we shall get ammonium nitrate. You see? Ammonium nitrate. So that is salt 2. Ammonium what? Nitrate. They are saying salt 1. No. That is not salt 2. Pardon me there. So this is salt 1. Salt 1. Then this salt 1, which is ammonium nitrate, is warmed with an alkali. Let's say if you warm this one, any salt of ammonia when you warm it with a strong oxidizing agent, I mean with a strong alkali, ammonia is going to be produced. So if I put sodium hydroxide, then we are going to have ammonia produced, then sodium nitrate. Okay, they are saying other products, a salt 2. So salt 2 is this one here, salt 2. Another product probably is going to be what? Water. Okay, because I'm seeing there's hydrogen and oxygen. What do you think this one is going to be? It has to be water. Is it even balanced when we look at this? This is 1, then plus 3. That will be 4 oxygens. This is 1 plus 3, 4 oxygens. You see that? Then hydrogens are 4, then plus 1. Those ones become 5. These ones are 3, then plus the 2, 5. And then nitrogens, how many are they? On the left, we are having 1, and then 2. Then here 1, and then 2 here. Okay, so it's balanced. The other product has to be what? Water. What else do we have? So the other products they are talking about are ammonia and then water. You see that? So salt 2 is sodium nitrate, you can see here. So our answer is B. Question 17. Mixing aqueous silver nitrate and aqueous sodium chloride produces a precipitate. Addition of which reagent to the mixture gives a colorless solution? Now, from silver nitrate, we have silver ions. Okay? Then you will add aqueous sodium chloride. We shall have the chloride ions there. And then you will form a precipitate, this one here. Okay? White what? PPT. You see? White precipitate. Now, this is a chloride in here, white precipitate. Now, addition of which reagent to the mixture gives a colorless solution. That means this one has to dissolve. Now, we have ammonia. In ammonia, we can have dilute ammonia. We can have concentrated ammonia. Okay, so we have chloride here. If it is a chloride, it can dissolve in dilute ammonia. Okay, even in concentrated ammonia, it will dissolve. Then when we have bromides, a bromide will not dissolve or dissolves sparingly, but we can say insoluble in dilute ammonia, but dissolves in concentrated ammonia. Then if it is an iodide, then here it is insoluble in dilute ammonia, and it is also insoluble in concentrated what? Ammonia. So there is this table in the textbook. You see, I can even show you where it is in the book. Let me show you. When you look at this book, I usually use this one here, and we go to group 17 here, that is for halogens, and we try to look out for that table. The table is here. Hope you can see it clearly. Sorry, we have this. So when you look at a chloride ion, color of the silver halide, so it's white precipitate. Then when you put it in dilute ammonia, it dissolves. If it dissolves, and even here it also dissolves in concentrated. Okay, then insoluble, the bromide is insoluble in dilute and then dissolves in concentrated. Iodide remains insoluble. You see? So that implies that when we go back here, our answer has to be aqueous what? Ammonia. As simple as that. Then question 18, which statement is correct? Barium oxide reacts with water at room temperature to form barium hydroxide and hydrogen. No, we are having barium oxide plus water, you actually get barium hydroxide. Group 2 oxides react with water to form a hydroxide. Okay, there is no evolution of hydrogen. Maybe when the elements are reacting with the water, we can put barium plus the water, then you get barium hydroxide, then plus the hydrogen. You see that? Then calcium oxide does not react with water at room temperature. This one is also wrong because calcium oxide can react with this water here, and then you get lime water, calcium hydroxide. So even this one is wrong. Then the third one, magnesium hydroxide reacts with steam to form magnesium oxide and hydrogen. This one is wrong. Actually, what reacts is magnesium reacts with steam. Okay? With steam to give us magnesium oxide and hydrogen. Okay? Then when magnesium reacts with water, cold water, the reaction is actually very slow, and it will give us just like these other ones. It is magnesium hydroxide plus what? The hydrogen. So this one is also wrong. That means our answer has to be D. Strontium oxide reacts with water at room temperature to form strontium hydroxide only, just as these ones here. So you're having the strontium oxide plus water, and then you get strontium hydroxide. As simple as that. So that one is correct. Question 19. Which statement about the properties of halogens and hydrogen halides is correct? Hydrogen and properties of halogens and hydrogen halides. Now, when I take you back to this book here, just up here, for hydrogen halides, okay, they are least thermally stable as you go down the group. What does this one mean? This one can break, okay? The bond can break in there, they can decompose, okay? Number one, we are looking at hydrogen, which is a smaller atom here. But then we see iodine, which is very big. So that means there is distortion in here, okay? There's a lot of polarity here, polarization, and you find that this bond here is weaker. You find that the charge on this iodine is distributed over a long what? Over a big volume. So the bond produced here is going to be weaker compared to chlorine. You have hydrogen and then chlorine, okay? They are small, so the bond here is stronger than here. And also when you look at these elements as you go down the group, they have the nucleus here. The electrons in the outermost shell are far away from the nucleus. So that means the nuclear attraction here of these bonding electrons and the nucleus here, it is going to be weaker compared to the one of chlorine, okay, when the distance is very small. So that means it is easy for these halides to decompose as you go down the group compared to up here, okay? Now let's go back to our question. So they are saying a chloride ion is a stronger reducing agent. This one is wrong. What is a reducing agent? A reducing agent is the one that produces electrons, okay? It gives electrons to another, and whatever receives the electrons gets reduced. Not so. Look at oil rig. Reduction is gain of electrons. So whatever receives the electrons is reduced. Then oxidation is loss of electrons. So a reducing agent gets oxidized in return, okay? Now when you look at, let's say this one here, iodine, it breaks down to iodine, hydrogen iodide, it breaks down to iodine, and then what? Hydrogen. Now here, the oxidation state of iodine in here is -1, but here it is 0, so it has been what? Oxidized. So that means this is oxidation. That means that we are having since this one is being oxidized, then it is a reducing agent. So that means as you go down the group like I showed you here, these ones become better reducing agents, stronger reducing agents, and then weaker oxidizing agents. Okay, so these ones here are good oxidizing what? Agents. Now I made a mistake, I think, here. So here they are strong oxidizing agents and weaker reducing agents. And then these ones are good reducing agents and weaker oxidizing agents. You see that? Now let's go back to here. By looking at chlorine, they are saying a chloride ion is a stronger reducing agent. No, it's a stronger oxidizing agent. So this one's off. Because look at these group 7 elements. These group 7 elements, they react by gaining an electron. Not so. And to gain an electron, that means you are being reduced. So it becomes easy for chlorine to gain the electron here because of the stronger nuclear attraction. Do you see that? But when you come to iodine, the distance here is too big. Do you see that? The distance is too big. That means there is a lot of shielding in here from the nucleus. So you are going to find that the nuclear attraction for this incoming electron is going to be very weak. So it is easy to lose an electron this way than to gain it. So if it becomes easy for you to lose an electron, then that means you are becoming oxidized. So therefore you are a reducing agent, because a reducing agent is the one that is oxidized in return. You see that? So that has to be that. Then let's proceed. We are having chlorine is more volatile. Volatility is the tendency to vaporize, to easily vaporize, okay, than bromine. Now, when you look at bromine, chlorine here to become a gas. So for these nonmetals, the more the electrons, then the stronger the ID forces, or the van der Waals forces of attraction. And the stronger the forces of attraction, then these ones can hold the molecule as a liquid or as a solid. This one is a liquid at room temperature. This one is a gas. Okay, so chlorine, they are saying, is more volatile than bromine. Yes, it is true. But what is the reason? Chlorine has stronger intermolecular forces. How can it have stronger intermolecular forces? And then it is a gas. The one that has stronger intermolecular forces is bromine. That's why they are able to hold it as a liquid at room what? Temperature. So this is off. Then hydrogen bromide is more thermally stable than hydrogen iodide because it has stronger covalent bond. This one is correct. Okay, remember I showed you here. Thermal stability decreases down the group. Okay, so this one is the least stable, so it breaks down much more easily compared to hydrogen bromide. You see that? So that means our answer is C. But look at the iodine is less reactive than bromine because iodine has weaker. This one is true, but this is not the reason. The reason is iodine here, it has the what? The reactivity of iodine of group 7 elements is in gaining what? The electron. You see that? But it has weaker what? Nuclear attraction for the incoming electron due to increased shielding. You see? So that is the reason. This one is correct, but the reason is wrong. So our answer has to be that C there. Question 23, statements about the chemical periodicity of period 3 oxides are listed. The maximum oxidation state of the period 3 elements in their oxides increases from sodium to phosphorus, then decreases from phosphorus to sulfur. Maximum oxidation state of period 3. Now the oxidation state of period 3 elements, what are we seeing? We have sodium, magnesium, we have aluminium, we have silicon, we have phosphorus, we have sulfur, and then we have chlorine. So the maximum oxidation state here is +1. This is +2. This is +3. This one is +4. This one is +5. It has 5 electrons in the outermost. It can lose all of them. It can front them for bonding. Okay. Then what else do we have? We also have here 6. Okay. And then this one can lose all the 7. You see that? So they are saying the oxides, they are saying the maximum oxidation state of period 3 in their oxide increases from sodium, that it increases from sodium to phosphorus, then it decreases from phosphorus to sulfur. It is increasing. So that is wrong. Okay. So we are going to have one of the oxides from sodium to aluminium dissolve in water without hydrolysis. Sodium to aluminium. Now, when I take you to period 3, we shall have sodium and magnesium dissolving to form hydroxides. Then aluminium will also form that hydroxide, but it will go on because aluminium here, 3 plus, is a very strong ion. You can see that the charge here is too big. Okay, it has a high charge density. The size is small, so charge density, we are getting the charge. The bigger the charge, divide by the small volume, then you are going to get what we call the high charge density. So this charge density now will cause these water molecules around them. Okay, the water molecules here, there is going to be an attraction. Remember this one, the oxygen is partially negative, then partially positive, partially positive. So this strong attraction here will cause this water molecule to lose a hydrogen in there. So it will weaken the bond between oxygen and hydrogen. Okay, and then it will release hydrogen ions in solution. You see that now aluminium here is reacting with water, and that is hydrolysis. You see that? So this one has to be wrong. They are saying without hydrolysis. You see? Then from silicon to sulfur, they are hydrolyzed by water. We know that silicon can react with water. Okay? Yeah, like silicon 4 chloride reacts with the water to give you the silicon 4 oxide, then plus those white fumes of HCl. Okay? Let me take you there. So periodicity is actually chapter 10 here. So when we go there and we look through, what are we looking for? Oxidation states, are they listed anywhere? Because that one we talked about it. So, okay, this is the one here. The oxides of sodium and magnesium react with water to form hydroxides. You see that? The presence of excess aqueous hydroxide ions makes these solutions alkaline. Very good. Now, what else are we looking for? The one of aluminium. Then they are saying that when aluminium oxide does not react or dissolve in water. It does not dissolve in water, which is why an oxide layer can protect aluminium metal from corrosion. However, it does react and dissolve when added to acidic or alkaline conditions. So that is why you are getting aluminium having amphoteric what? Being amphoteric. When aluminium oxide reacts with an acid, it behaves like a base. It forms a salt, okay, with dilute sulfuric acid plus water. When it reacts with an alkali, it behaves like an acid, reacting to form sodium tetrahydroxoaluminate. Okay, and then compounds that can act as both acids and bases, such as aluminium, are called amphoteric. You see that? So that aluminium, I want to show you how it produces an acidic what? Reaction. Yeah, that is around here. So when it dissolves and then it forms this aluminium oxide, okay. Uh, okay, this one is coming from the dimers, aluminium chloride. Here, this one here. When you dissolve it in water, it is going to break down that dimer, and then we're having the aluminium ion in water. So aluminium ion is not going to be just like that. It is going to have 6 water molecules around it. Okay. Now look at the explanation here. Once we add the water, the dimers are broken down and the aluminium ions and chloride ions enter the solution. Each relatively small and highly charged aluminium ion is hydrated and causes a water molecule bonded to it to lose a hydrogen ion, thus turning the solution acidic. We can show this. You see that? So in there, it is reacting with the water there, and silicon 4 chloride reacting with the water, then you get this insoluble oxide, and then plus the hydrogen. Of course, this is silicon 4 oxide. There was a mistake done here. This O is not there, okay? So that is that. So here we are putting this one off. That means 3 only has to be our answer. So the answer has to be D. But what does it say? The structure and bonding changes from giant ionic to giant covalent to simple molecular. That is true. Let me take you back here. So when we go back here to the structures, you can see that we are seeing giant ionic, giant ionic, giant ionic. Then here you have giant covalent, then simple molecular structures for these one. As simple as that. Okay. So that is what we are having there.